Welcome to another Forge College Explainer. Today, we're essentially putting on our lab coats, securing our safety goggles, and stepping right into the laboratory. If you've been following our From EVM to SVM track, you know we've been setting up a pretty grand mission, comparing Ethereum's EVM apples to Solana's SVM oranges. Now, to do that fairly, without causing a statistical explosion, we need a highly controlled experiment. We're taking that theoretical methodology we previously discussed and finally putting it into practice.
Here's our blueprint for today's session. We'll be moving through 5 distinct phases: the grand blockchain experiment, gathering the telemetry, executing the benchmarks, cleaning the messy data, and finally arriving at our ultimate prize, the final comparison table. Let's get right to it.
Okay, let's dive into part 1, the grand blockchain experiment. When we talk about benchmarking blockchain performance, especially when real money and heavy computational resources are on the line, we literally cannot rely on guesses. We need absolute laboratory-level strictness. So our definition of a controlled benchmark is all about creating a reproducible scenario where we run identical operations under perfectly consistent conditions. Why? Well, to isolate the execution costs from external network noise. Think of external network noise like living with a completely chaotic roommate who decides to turn on the microwave, the vacuum cleaner, and a hairdryer right at the exact moment you're trying to measure a delicate electrical current for a physics experiment. It throws all your readings off. We have to isolate our environment to ensure we're only measuring the machine itself, not the chaos going on around it. To actually achieve that isolation, we break our experiment down into 3 variable groups: fixed controls, input controls, and experimental factors. Think back to a classic science fair project. If you want to know which brand of fertilizer makes a plant grow the tallest, well, the fertilizer is your experimental factor. But to prove it works, you have to ensure the amount of sunlight and water, which are your fixed and input controls, remain exactly the same for every single plant. In Web3 benchmarking, if we want to measure differences in smart contract execution, we have to lock down the network topology, the node versions, and the payload sizes. This guarantees any difference in cost is strictly due to the architecture, and not just because of a sudden spike in network congestion. Moving right along to section 2, gathering the telemetry. Now it's time to set up our measuring instruments and collect incredibly precise data points while our experiment is actually running. The crucial thing here is that we must deploy 3 layers of data instrumentation. First up, we need transaction metrics directly from the node itself. Second, resource telemetry, which basically means tracking the CPU and memory usage of the machine running the node. And third, client timing, which captures the exact timestamps of when a transaction is submitted versus when it's actually included. This brilliant setup gives us a complete X-ray picture of what's happening under the hood. We aren't just looking at the final receipt, right? We're actively monitoring the engine's temperature and fuel intake as it runs. Now, since the EVM and SVM effectively speak entirely different technical languages, we need a Rosetta Stone to make sense of the incoming data. That's our canonical mapping table. We take the EVM's gasUsed and Solana's compute units and map them both to a neutral canonical field we call gas_or C_U. We map the effective gas price and Solana's fee to a unified fee_charged field. Doing this ensures that downstream, when we're comparing these platforms, we aren't getting completely confused by their specific terminologies. We translate the whole shebang into one unified neutral dataset.
All right, part 3, executing the benchmarks.
This is the fun part. We're finally firing up the lab equipment to run our carefully designed tests. To do this correctly, we follow a strict procedural workflow. Step 1, select the environment. We strongly recommend a controlled local fork of the network to minimize external variables. Step 2, prepare the artifacts. So getting your compiled bytecode for EVM or your BPF programs for Solana ready to deploy. Step 3, set up instrumentation, deploying those lightweight metric exporters and transaction generators. And step 4, execute the scenarios. Following this step-by-step approach absolutely guarantees that our experiment is perfectly reproducible by any other engineer who wants to double-check our work. During execution, you have to decide on a sampling strategy. The 2 main ones are dense sampling and stratified sampling. Dense sampling is kind of like throwing 100 ping pong balls at a target all at once. It gives you a massive volume of data quickly, but it can cause collisions and transient network congestion. Stratified sampling, on the other hand, is like throwing those ping pong balls one by one, carefully grouped by size. For cost modeling, stratified sampling is a real game changer, because it helps us isolate the exact effects of the payload size or instruction count, completely avoiding the noise of artificially created traffic jams. Which brings us to Section 4, cleaning the messy data. Let's be honest with ourselves. Every mad scientist inevitably spills some chemicals on the workbench. The real world isn't perfect, and sometimes we have to clean up the lab. So what happens when our data is messy? Well, in real network conditions, nodes will occasionally drop connections. RPC endpoints will time out, and sometimes your telemetry will just return a random string of zeros because a logger was misconfigured. If we ignore these errors and just blindly feed this garbage into our cost models, we're going to get garbage results out. It literally invalidates the entire experiment. That is exactly why we enforce a rigid cleaning protocol. We validate every single field and timestamp. We flag improbabilities, like if your record shows a gas usage that is somehow higher than your actual gas limit, yeah, that's a massive red flag. We also reconcile missing data by cross-referencing our raw node logs. But here is the absolutely crucial part. You must log all corrections. Actually, scratch that. You must maintain a fully auditable cleaning log. You can never just silently delete bad data points. You have to document exactly what went wrong and how you fixed it, or if you had to replace it with a rerun. Transparency is the bedrock of good engineering.
And finally, Section 5, the final comparison table.
This is the moment we produce the ultimate engineering artifact, based on a practical, real-world scenario. Let's look at a worked example to see this all in action. We're going to compare a standard ERC20 token transfer on the EVM against an equivalent SPL token transfer on the SVM. Because these operations are functionally identical, they both just debit one balance and credit another, they serve as a perfect structural baseline for our comparison. To guarantee an absolute apples-to-apples comparison, we lock our scenario parameters down tight. We mandate exactly 32 bytes of memo data per transfer. We use a single-threaded client to submit the transactions. We run exactly 200 trials per platform, and we enforce a strict 200 millisecond delay between each trial. By enforcing these rules on our local network forks, we essentially reduce environmental interference down to zero. So what do the raw results actually look like? For our simulated EVM trial, we capture a gas-used measurement of exactly 52,412. By dynamically pairing this raw usage metric with our controlled effective gas price, we can accurately calculate the total native fee in ETH. Over on the Solana side, that identical logical operation yields a measurement of 145,300 compute units. This completes our raw data picture. But notice, these numbers are vastly different and represent entirely different units of measurement. This perfectly illustrates why gathering the data is only half the battle, and why our normalization step is just so critical. Once we've matched and cleaned all 200 trials, we finally create the artifact, our validated canonical comparison table loaded with derived fee and timing fields. We should celebrate this. This pristine, perfectly clean dataset is the exact empirical bedrock we need. We've taken messy, chaotic reality and distilled it into pure, reliable information. Let's quickly summarize the core takeaways from today's blueprint to make sure we've locked in those non-negotiables. First, explicit variable control is the absolute foundation of a defensible comparison. Second, you must use three-level instrumentation to map platform-specific quirks into a universal canonical schema. And third, data cleaning must be completely procedural and highly auditable. If you master these three rules, your benchmarking is going to be bulletproof. Which leaves us with one final exciting question. How exactly will we use this raw telemetry to build universal cost models? Like, how do we turn that table of numbers into actionable insights? That is precisely what we'll tackle in our next explainer, modeling and normalizing costs. Until then, keep questioning, keep testing, and keep building. Remember, this explainer was proudly brought to you by Forge College. Be sure to head over to forge.college to dive deeper into this subject and to explore a whole range of other fascinating Web3 topics. See you in the lab next time.